you. All right, one of our final looks at the calendar. Today we cover something called the Sierpinski Gasket. It's related to the Koch snowflake that we talked about last time, and it's just more stuff on fractals. Next class is a TBA day. That's built in just in case there's a snow day. And if there isn't a snow, well, here's my plan. My plan is to review for the test this coming Wednesday. And then if we have an extra class, then we'll review, and I'll bring in some other fun math stuff that we can do that isn't on the test. But I've got a little bit of flexibility just in case we have a class cancellation, which we haven't. The financial project is due. I've already gotten them from a bunch of folks. So if you haven't turned it in yet, hopefully it's in the folder. Otherwise, get it to me ASAP. Late penalty points start to add up as of today. All right. At the end of today, it is late. And then our test is on December 18th. When is that? Wednesday? A week from Wednesday. This class will be officially over. Any questions on the calendar? Oh yeah, good point. I think that I can come in like maybe at actually we're going to keep it at 1 o'clock because some people have tests until 12:30, but I can stay later on the other end. So we'll make sure folks have enough time. But get here on time at 1 if you want some extra time. Good question. Okay, so we'll start here at the top of page 32, and we will go to Kate. Sierpinski. Okay, thank you. So here's a picture of the first few steps of this thing called Sierpinski's triangle or Sierpinski's gasket. So we start with a seed triangle, just any old ordinary triangle. In the pictures below, it's going to be an equilateral triangle, but it doesn't have to be, like in this picture here. And then you remove the middle. The middle is in quotes here, so it's not really clear. It's got to be something more precise than just saying remove the middle. So what you do is you go to, what's it called when you go to the middle spot on a line segment? What's the name of that dot? The geometry word starts with an M. Not median, but it's kind of related. Midpoint, we've heard this word before. Yeah. So what we do is we go to the midpoint of each side. Yes, midpoint of each side, right in the middle. And then you connect the dots and you come up with some triangle. And that triangle is the triangle I'm talking about taking out, all right? So it's very well defined, even though it's not written there. You go to the midpoint of each side, connect the dots, take that triangle and pull it out. And so now it's white in the second picture. And then in the second picture, we actually now see that there are some more triangles. So for example, in this top triangle, which is now like its own triangle, you take out the middle, which means you go to the midpoint of each of the three sides. And then what? And then connect the dots. And that triangle gets removed. And that's the triangle that's missing right here. And we do that same thing in each of the other three shaded in triangles. There. And we remove the middles and we get this new picture, step 2. And then we do it again and again until we're tired of it. All right, and we get this shape that is kind of gradually whittled away, and we get all these pretty triangles of different sizes that are cut out of it. All right, let's go to Aileen after. Okay, so there it is, starting with an equilateral triangle, and you can see some of these different triangles that have been cut out. So for example, this big one here is the very first one that was cut out from the original shape. And then you can see, I'll put in a different color, some of the next triangles that got cut out, those three right there, yeah? And can you see what the next layer of triangle is that's cut out? Like just go find the next biggest triangle that's not highlighted yet. So for example, in blue, there, and there. And then the same thing down here and over here. Okay. And so that's as far as we got up above, but you can carry this forever. And if you carried it anymore, you wouldn't be able to see a difference here because there's not enough pixels on the screen or on the paper to tell that it's any different. All right, let's go to Jake. Thank you. We'll go to number 1, Ed. All right, 3 characteristics of our self-similarity. So here in the left-hand picture is the Sierpinski's gasket. And if we just blow up this triangle right here, enlarge it, it looks like that, which looks an awful lot like the Sierpinski gasket, right? And so this is the self-similarity thing that we saw before. You keep zooming in and it keeps looking the same. And if you took, for example, this little tiny thing down here, not the entire blue one that we took before, but just this little tiny 1/3 of the blue one, and zoom in, and it'll look exactly the same. And it looks exactly the same forever. And it's perfectly self-similar. We'll go to number 2, Mary. Okay, so let's pause there. Taking a look at my orange triangles up here at the top, I'm just going to we're going to ask some questions about the perimeter of this shape as we go further to the right. Now, perimeter normally just means add up the sides around the outside. So for example, the perimeter of this original would just be that length plus that length plus that length. But now when we go to the next step, it's still blue plus blue plus blue, but if I'm trying to look at all of the edges of this shape, then it has 3 more edges that weren't there before. It's this stuff in here that's now physically edge in this shape, even though it's not around the outside anymore. So we're going to add those things. So did the perimeter get bigger, smaller, or stay the same? Got bigger by whatever the red is. And then in the next shape, we still have the red thing there. We still have the original blue thing there. But then we have to add the lengths of those 9 edges, right? And so the perimeter keeps getting bigger. And getting bigger could mean the perimeter becomes infinity, or it could mean that it levels off at some number. Like maybe it will never get above 100. Like it's getting bigger, but maybe it's getting bigger by teeny and tiny amounts. So those are the questions we're going to answer first. So let's move on to, we'll keep going with Mary for the last part, please. Even though.
We don't have that at all. Yeah, we don't have not at all.
No.
Not even on the page.
Super. All right, let's go to Brandon then.
We don't have that either.
So what do you guys have? What are you doing? Assume what happens to the perimeter. Yes, we got that. And oh, is the diagram just a little different? Oh, it's the same. It's the same. It's the same. I just have it going across horizontally. You guys have it going vertically, right? Okay. So we're going to assume that each side of the seed triangle is 1. That's the original triangle. So 1's on each side. So what's the length of the boundary, the perimeter? 3. So I'm going to call this one, I think we're calling it P0. Original perimeter is 3. Okay, then we look at the next step, step 1 here. Now we still have 1's going all the way around the sides, but then we have new shapes, or new sides, I should say. Anybody have a guess as to how long the length of that green line segment is? It's a half. It's exactly a half. It's half of whatever this one is, whatever the parallel one is. This is a geometry fact that you might have seen back in high school geometry, but if you connect midpoints, the length of the line segment you get is always half of the parallel side. So erase this guy. So this guy's a half here. This one, because it's an equilateral, is also a half. It's a half of this bottom one, which is a 1. All right, so they're each a half. So 1/2 here, and then 1/2 here. So yes, so then the P1, and we're using our notation for sequences, it is 4.5. I'm going to write it this way. I'm going to write it as 3 plus, what am I going to say? I'm going to say 3 plus 3 halves, right? You got 3 sides, each of which is a half. It's really hard to see my green halves in here, so let me change colors. Okay, that's better. Okay, looking at the next shape, I'm gonna, let's use a different color here. So P2 equals, all right, So the boundary still is the same as it was before, right? We have everything else plus. Okay, so I'm just going to copy the other things. 3 plus 3/2. And there's nothing wrong with writing 4.5, but I'm trying to capture a pattern here that will be hidden if we write it as 4.5. Plus. Okay, now I'm going to highlight in purple all the new shapes that we need to find the lengths of here. Yeah, each of those is a quarter. It's a half of a half. That's what it is. So this is a quarter, and they're all a quarter. So how many quarters do we have? 9 of them. 9 different line segments at that stage. Do we see it? Each of them is a quarter. So this is 9 quarters. Okay, and then one more. P3 equals. It's everything I had before plus some stuff. So I'm just going to copy first. Okay, and I'm going to take my time here. I'm going to grab all of these triangles that are new. It's just these teeniest, tiniest ones here. And so the first question is, how long is each line segment? Each individual one? They're eighths. So it went from a half, to a quarter, to an eighth. Every time it's half what it was. And how many of those green line segments are there? There are 27 of them. So if you have a lot of patience, you can sit there and count. If you're like me and don't have as much patience, you can try to use some symmetry. For example, how many triangles did I highlight up there? Yeah, Casey? Yeah, so Casey's recognizing this pattern that we have here. We had a 3 becomes a 9, and it seems maybe natural that we're just multiplying by 3. Right. Yeah, so different ways to figure out how many exactly there are. I think we decided on 27, and each of them is an eighth. Okay, so let's see if we can fill in here. All right, so Brandon, do you have this thing written down based on? All right, go ahead. Okay, so we're actually going to write both here. So let's start with the recursive one. So I'll do this one here in black. Remember, recursive has a starting one and then a generic formula that references the previous term. So what's the starting boundary or perimeter? It's 3. Okay, so that's just given. But then we need to capture the formula. Now, the formula almost always has what as the next thing that's written? Pn minus 1. That's our way of referencing the term that's one before, one earlier. Okay, what was the basic operation that we did to get from one term to the next? There's addition, subtraction, multiplication, division. It was addition, wasn't it, on the previous term? I mean, there's fractions in here, but the very first thing I wrote down was all of that, and then a plus. So I always took the previous answer and I added something to it. So it feels like that's what we got to do here. Previous answer plus something. Now it's tricky to figure out exactly what the plus is supposed to be. Okay, so let's see if we can figure out what that plus is. So plus. Okay, so take a look at just the individual terms now. Just the individual ones. I need to find a different pattern just in those fractions. And I think this is kind of what Casey was getting at here. What's the pattern on the bottom? Is keep multiplying by 2. What's the pattern on top? Is keep multiplying by 3. And so really the whole pattern is multiplied by what single number? It's a fraction. Is 3 over 2. That's really what's happening, is we're multiplying each fraction by 3 over 2. And if I say, hey, keep repeatedly multiplying by a number, that's just an exponent, right? Like if I just said multiply by 5, 5, 5, 5, 5, that's really 5 to some power. So this is really 3 over 2. 3 over 2 to some power. We just got to get the power right. Let's look at this guy right here. 9 is really 3 squared. 4 is really 2 squared. The powers were both 2. All right, what is this? 27/8 is really 3 to the something, 3 cubed over 2 cubed. Agree? So here the powers are 3s. There the powers were 2s. What's the relationship between the power and the subscript? Power and the subscript? They're the same. So that's going to be an n. And that's our formula. Okay. Is this a good test question? I don't know. I'm not convinced. I mean, it's hard to ask test questions where I say, hey, find a pattern. Because if you just see it like that, fantastic. But you could also not see it and spend half an hour staring to try to find this pattern. So I guess really what I like about this example is that it brings back again some of the ideas of our sequence notation and this concept where we just keep taking the previous perimeter and adding something. Okay, that's exactly what recursive talks about, is do something to the previous answer. And then we got our exponential stuff in there, which was, you know, we've got our exponential sequence here in blue on the wall. Just keep multiplying by 2 to go along that bottom row. Here, just keep multiplying by 3/2. Okay, so that's fine, fine, fine. Recursive is good enough. I'm not going to write an explicit one for this guy, but you're welcome to think about that if you wish. And then let's answer this follow-up question. What happens to the length of the boundary as n goes to infinity? You keep adding 3/2 to the end. So we added 3/2 and then 9/4 and then 27/8. What would the next one be? 16 on the bottom. $81 is good. So add 81 over 16. Okay, and then just in terms of these guys as decimals, 3 over 2 is 1.5. This next one here is 2.25, right? This next one here, 3.375. So we're adding 1 point something, we're adding 2 point something, we're adding 3 point something. You are adding bigger and bigger somethings. And if you do this forever, what will you get to? Infinity. So the perimeter is infinite. What happens to the length of the boundary? It approaches infinity. Okay, so that's what the perimeter does. Let's think about the area. What happens to the area every time we start taking out these triangles? They get smaller. Smaller towards what number, do you think? So the total area of what it... Yeah, let's see. So the total area of this guy, I'm just going to throw out a number. Let's say the area of this original triangle is a half, 1/2 square units. Okay. So it's going to get smaller, smaller, smaller as we go to the right. What will it approach? Will it approach like 0.2? Will it get down to like 0.01? Will it get smaller than 0.01? How small? Smaller and smaller decimal, not exactly to 0. But there's this kind of instinct that says, hey, it's going to get as close to 0 as you have the patience to get to, right? All right, so let's see if we can solidify that a little bit. Okay, here we go. Part A. Let's go back to Casey for A. Okay, so you have the seed, and then you're taking out that middle part. What part did you take out? What fraction of the original triangle did you take out? Is it a half? Is it a quarter? It's a quarter. It's 25% that we took out. And if you look at it, you might be able to convince yourself that even though I've drawn 3 triangles, there are actually 4 triangles, counting the white one in the middle. And all 4 of them are exactly the same triangle, just flipped around a little bit for that one in the middle. So each of them has exactly the same area. And the area of each of these 4 triangles is just a quarter of the original triangle. So when we remove the middle triangle, we're taking away a quarter, which means what fraction is still there? 3/4, right? 75%. So what fraction of the area remains? 3/4 or 75%. Let's go to Griffin for B. Okay, so now we're taking out smaller triangles, but there are 3 of them instead of just 1 of them. So here's what I like to do. I'm just going to focus on this triangle up here at the top compared to what it originally was. Just for that top purple triangle, the original, what fraction did we take out? When we took 1/4 of it, right? Even though the purple one is smaller than the original orange, we took away 1/4 of it. So that purple one became 3/4 of what it was. But that purple one exists down in the bottom left and in the bottom right as well. So everything that you had before becomes 3/4 of what it was. So what fraction of the area still remains over here is 3/4. Right? Because every part of the shape gets 3/4 remaining when you take stuff out. Does that make sense? I think there is another way, like maybe a more direct way to go about calculating it, but I think it's complicated. Thinking about the original triangle, what can you say about the small red triangle? What fraction of the big red triangle is the small red triangle's area? Is it 1/8? Half? Comparing the small red triangle to the big red triangle. Is it 25%? Third. Fourth? Okay, so I'm going to start drawing in all these red triangles. So how many red triangles are up there? Altogether, there are 4 of them, including the white one in the middle, right? So there's 4 red triangles up there. How many red triangles could you fit in here? Another 4. How many down there? Good. And how many in this white space in the middle? Also 4, right? So the original triangle, the entire thing, has how many little red triangles in it? It has 16 of them in it. So when I just look at this little red guy compared to the entire, maybe it's better without the hole in it, the entire shape, that little red thing is 1/16 of what it started as, right? It's 1/16. Okay, so we took out 1/16 up there and we took out 1/16 there. So how many 16ths did we take out? We took out 3/16. But here's the complicated part. You took out 3/16. I don't know how to say this. We didn't have this original triangle here in the middle, right? It was just an empty hole. And so, yes, we took 3/16 of the original, but it turns out we only took 3/4 of the one that we had before. I don't know how to explain it because I don't think of it that way. I think, like I said, there's a direct way to count it, but I much prefer just look at one piece. Okay, if we're all convinced that this top black thing and the new black thing, that the new one is 3/4 of the old one, then we should be convinced it's 3/4 all the way around. Okay, looking at part C, which is just the same thing but one more step. Yeah. Then, for example, I will highlight in black here this top triangle compared to the new top triangle. What fraction of the area is still there in the new one compared to the old one? It's still 3/4, and it's 3/4 everywhere. So, for example, you could have drawn this triangle and this one down here, and it's 3/4. Everything becomes 3/4. So what fraction of the area still remains? It's 3/4. And so now we can do part D. Where are we now? We'll go to Evan. Okay, so let's give this a shot. So I'm going to use A for area. So we'll do the recursive one first here in red. Here. It says assume the area of the seed is 1, just to make a nice number there. And again, in the recursive rule, what's the first thing we write? Is a n minus 1. It says do something to the previous number. What happened to the area every time? You did subtract 1/4, which means we kept what fraction? 3/4, right? Take 3/4 of whatever you had. What operation says take? Does it subtract?
Divide.
keep 3/4 of whatever you had. Let's multiply. The new thing is 3/4 of the old thing. Okay, and then in blue here, we'll do our explicit. A sub n equals. Okay. The idea here is that we are multiplying by the same amount every time. Multiplying by 3/4 every time. So we had two kinds of sequences that we really studied a few weeks back. We had sequences where we kept adding the same number every time, like in that trash example where we added 5 tons of waste every year, or examples where we multiply by the same number every time. This is multiply. First guy was called linear. This one we're talking about here is exponential. And so I'll just remind you of our exponential formula. This is in packet 2, but it said you do the start amount times the common ratio, that's just the multiplier, raised to the n. This was our formula from the previous packet. What's the start amount for the area? Is 1 times the ratio is 3/4. That's what you multiply by every time, raised to the n. That's it. Okay, and what happens to the area looking at that 3/4 now? It's got to go to 0. You keep taking 3/4, 3/4, 3/4. Eventually it gets within a hair of nothing. Casey said correctly, it never gets to 0, but it gets as close as you could possibly imagine to 0 without ever getting there. The longer you wait, closer to 0 it will be. So we will say it goes to 0, but technically never gets there. All right, conclusions. All right, Griffin, did you read? All right, let's go. Let's go around to Sam, perimeter. Okay, good. So we've got the recursive form. We just have different versions, like they're, yeah. All right. So the recursive version, maybe you need to update yours. Huh? Recursive version is exactly what we wrote down there, and the explicit version apparently is written out there. At one point, we thought it was not worth the trouble, but there it is. It's worth the trouble now. And then the area formulas, we just wrote up above both of these things. All right, so let's keep going to Sam for our conclusion here in C. Okay, great. Stephen? Okay, these are two things that kind of seem contradictory, the two of them together, but they're both true. The perimeter, the length of the boundary, heads to infinity, but the amount of space that it takes up heads to 0. So there's like this infinitely long walk out there, but ultimately it takes no real estate to actually have this walk like a path built in. So for example, let's take a look at the two pictures at the bottom. We've got, you guys have these, right? Yes. Okay, so for example, here in Western Massachusetts, you will find a lot of TV satellite dishes. And the idea is that you got this TV signals coming in from outer space, right? There's a satellite up there transmitting this information to the dish. Now, this is the receiver. Just that dot right there is the receiver. Now, in terms of these like TV waves coming in, not very many of them are going to perfectly hit that little receiver, right? So instead, we build up this dish behind it, and we say, okay, this dish is going to catch a lot more stuff than just the little receiver, right? And the dish is going to catch all that information and it's going to bounce it back. The waves are just going to hit it just like it's a wall and bounce back. And the dish is built in such a way that all of these things bounce perfectly back to the receiver. And so they put that receiver not in just any random spot, but they put it in the spot that is the focus of all of these rays coming in from outer space. Great. But even more than that, even more than that, we want to be able to capture not just stuff that perfectly hits the receiver, but maybe we can get a little bit better reception, more quality, if we have more space, more antenna for all of these TV rays to come in and hit. And so the question is, what shape should we make this antenna? And you guys have seen like literally rabbit ear shapes coming out of the TV. Or up on the roof, you might have just like a big pole with like some crisscrossing, you know, kind of metal rods, right? Just trying to get a bigger area, sorry, a bigger space for the satellite rays, to the TV rays to come in and hit. But really what we want is something with a big perimeter, because we want a lot of things for the TV rays to come in and be able to hit, but we don't want it to take up a lot of space, right? And you can't just have like a football field worth of antenna coming out of your house. And so we want something with a lot of perimeter, but very little area. And the Sierpinski gasket accomplishes that, right? It's got area that's very small. It's a very tiny amount of space that it's taken up, but the perimeter is very large. And so it makes sense to make your antenna kind of in the Sierpinski gasket shape. And what shape is this? Does that look like? Looks like a snowflake. It's the same idea. The snowflake takes up not very much area, but has a large perimeter. And so that's something that's good if you are making a satellite dish or an antenna. Okay, so we got that. Also, this kind of Sierpinski shape happens in some seashells. You guys seen this kind of seashell before? Yeah. And so if you look real close, it's probably hard on the image that you have, but on the image that I have here, we see little triangles and bigger triangles and medium-sized triangles, and all these triangles cut out, and it's not going to be perfect, but it looks an awful lot like this thing that we're modeling with the Sierpinski gasket. Okay, let's go to the next page. Yes. Okay, chaos game. All right. So. Let's go to 7. Who's our reader now? We'll go to Chad. Okay, let's pause there. All right, so we've got our triangle, and we've arbitrarily decided that the 6 different faces of the die are going to get matched up to the different vertices like I've drawn here. Okay, so then we'll go to Jeremy for 1. Okay, so everybody just put a dot someplace in the triangle, on the triangle's border, outside the triangles, okay. Really anywhere is fine. Just put any dot any place. Okay, and then we roll the die, and the die is going to say some number 1 through 6. Let's suppose that the die says the number 3. So which vertex is 3 for us? Is B. We just decided that 3 and 4 is up there. So what we're going to do is we're going to put a point halfway between our current location, which is my blue dot here, and the vertex that we're supposed to head towards, which I said was B because I got a 3. So wherever you are, what I want you to do is estimate halfway between your dot and vertex B. Now you might still be outside the triangle, you might be on the triangle, I don't know where you are. But just put a dot right there halfway between. And in order to make it easier for us to follow, let's number these guys. Put a 1 next to the first guy, 2 next to the second guy. Okay, and now we're going to roll the die. Damien, what number comes up on the die? Damien says 6. 6 heads us towards which vertex? Is C. So halfway between the current dot, which is number 2, and vertex C, you're going to put another dot. I'll use a different color. Estimate like halfway between. Call that 3. Okay, and then Kate rolls the die. Kate, what did you get? Kate says 2. Which vertex is 2? A. So halfway between your current dot, which is number 3, and vertex A, you put a new dot, and we'll call that 4. Okay. So we got these 4 dots, and we all have them in different spots depending on where we started. And they would also end up in different spots depending on how you roll the dice, right? So there's a whole lot of like randomness in this problem. We each picked a different starting point, and then we roll dice. Now we're all saying we got exactly the same thing, but we're probably going to get different things when we roll the dice for real. Now, it turns out in order to see what we need to see, you have to do this for a long time, longer than we have time to do here. So we're just going to jump to the punchline. But you would imagine, or at least I would imagine, that we would just get this very chaotic behavior with randomly spaced dots floating all around willy-nilly inside and around this triangle. I wouldn't expect to see really anything nice pop up. Okay, so there's a website that I'm going to encourage you guys to check out later. And I'm going to pull it up here. So if we scroll down past the non-working applet, we get this. This is the shape that we would have if we just started putting dots all around, it would look like this, which we now have a name for. What is it called? Sierpinski's gasket or Sierpinski triangle. Now, you might have an isolated dot. Oh, I can't draw on this, but you might have isolated dots like randomly here, there, and everywhere. But ultimately, if you let this thing run for 1,000 dots or 10,000 dots, you will see very distinctly this shape coming up before your eyes. Damien. I don't know whether or not the triangle has to be equilateral to start, but that's a great question. Yeah, the Sierpinski's gasket is defined for any triangle, so it doesn't need to be equilateral. I'm hoping that the starting triangle here also doesn't need to be equilateral triangle, but I don't know.
So it's always a triangle?
We start with a triangle for this one. There are other shapes to start with, like in the homework you started. Did you do a square one?
We did.
Yeah, so there are other shapes defined differently that can start with different shapes besides triangles. Yeah. Chad, did you have a question? No. Okay. This is a surprise, yes? You're doing this random thing, and out of no place, out of this chaos, pops up Sierpinski's gasket. Okay, let's move on to the next one here. Something called Pascal's triangle. So here is Pascal's triangle. Raise your hand if you've seen Pascal's triangle before. Just a couple, that's fine. Okay, so there are a lot of patterns inside of this triangle. Pascal was the name of a philosopher or mathematician back in the, don't quote me on this, 15th century. And so there's this triangle that he studied. He didn't actually invent it, but his name is associated with it. So the first basic idea is, can we figure out what the next row of numbers is? So with your neighbors, this is not an easy question, but with your neighbors, can you investigate each row, one row at a time, see if you can fill in the next row at the bottom? Okay, do we have that bottom row filled in? It's okay. So basic definition for this triangle is you just put ones on the diagonals all the way down. It's part of the definition. And then we just do this adding thing to figure out the next number that goes below. Okay, now there's lots of crazy stuff happening here. So one thing I would like you guys to do first is find these, and you can use your calculator for some of them. But I just want to think about these powers of 11. So first one actually is easy, but people don't all know this rule. But any number to the 0. Feels like it should be 0, but it's 1. It's kind of a weird definition, but any number to the 0 is 1. How much is 11 to the first? That's just 11. That's easy. 11 squared, some of you probably know. 121. Okay, 11 cubed probably nobody knows, but we can type it into the calculator. 1,331. Good. 11 to the fourth. 14,641. Yeah? So we just type them into the calculator. What do we see? Within the triangle. Like if you look at that 14,641, that's one of the rows of the triangle. Just look at the digits. 1, 4, 6, 4, 1. See it? So the problem, the reason that I stop, so go ahead, type 11 to the 5th, and you're going to be disappointed. So let's get 11 to the 5th here. What is that? 161051. That, right? Okay, what happened? It didn't work, right? Oh, well, part of it worked. Let's see. Is this one okay? All right, is it 5 okay? So I'm comparing here to this. Okay, those are good. Is the 0 okay? Well, it's a 10, but then we're going to carry a 1. So I like the 0. It's a 10, but we're going to carry a 1. What's the next number? After the first 10 is another 10. It's a 10, but we're carrying the 1 from before, so it's now an 11. So this 1 right here is the second number in the 11, and we're going to carry a 1. What's after the next 10? Is a 5, but we're going to carry the 1. So it becomes 6. It works. It works forever. But it's not going to be as satisfying because carrying makes it so that, I mean, it just can't look. You can't have a 10 in the middle of your number. Right? You can have a 0, carry the 1. Yes? So if we have, all right, so what you guys, how can we write this? When we wrote this 1, 3, 3, and 1, we were really saying that in the tens place, and in the hundreds place, and in the ones place, and in the thousands place, we had these numbers. You had a single thousand, you had 3 100s, you had 3 tens, and you had a 1, right? And if you just write that number, you'd say, oh, it's just 1,331. Let's keep going. Let's go down to the purple. So I'm going to extend a little bit further. We have some 10,000s, and we have some 100,000s. And I'm going to write down the purple numbers. 1, 5, 10, 10, 5, and 1. All right? Okay, so how many ones do we have? We just have a single 1 there. How many 10s do we have? We have 5 10s, so that's, well, maybe I'll write it this way. There's a 1, and there's a 50. How many hundreds do we have? I have 10 hundreds, which is better known as what? As 1,000. So you see how we're off by a digit? Like it's the digits, that number just got bigger by 2 digits instead of just 1. Next one, that was 10 hundreds. Then we have 10 thousands. So 10,000. 10,000 is that number. What's the next number? 5 what's? 5 10,000s, which is 50,000. And then finally, 100,000. So in terms of carrying, okay, that 1 is fine. That 5 is fine. This guy right here, I really wanted it to be a 10, but 10 doesn't make sense in the middle of this arithmetic problem. It's a 0, carry 1 into the next column. So that's the 0 all down here. And then all these should be zeros, but we had to carry the previous one. And so that's this first kind of outlier. Okay, next thing I want you guys to do is I want you to add up all the numbers in any row. So for example, 1 plus 2 plus 1 is 4. Go through all the rows, including the one that you made up at the bottom, and find out what the sum is. Okay, so it's all right if you haven't done all the way through, but hopefully we see a pattern with just the first few numbers. What's the pattern? These are just times 2s. What color are these numbers on our walls? These are the blue numbers. We don't have the 1 in the very beginning, but starting with 2, 2, 4, 8, 16, 32, it's exactly those numbers. The red row that you guys came up with was 256. Somehow, for some reason, adding these guys up just gives you the powers of 2. That's cool. Let's take a look at this next one. I'm going to go here and then 1 out. So that is not going to work. Here and then 1 this way. All right, this is called the hockey stick theorem. Yes? Hockey stick. I want you guys to add the numbers on the long part of the hockey stick. Just the long part of the stick, not the slap shot part. Just the long part. The handle is 20, which is exactly what is on the other part. So what I'd like you guys to do, in order for this to work, all you have to do is pick any of these spots right here or on the other side. Go as far as you want, and then just 1 number at the end. So pick a random spot to start from. Go into this triangle as far as you want, and then just curve 1 number at the very end and see if your hockey stick theorem is still true. Okay, So Pascal's triangle has lots of stuff happening in it. We are just scratching the surface on this shape. If you are intrigued, there's plenty of reading you can do about this list of numbers. Together, we're going to do this activity here. All right, so here's a few more rows of Pascal's triangle. You can see the numbers get pretty big pretty quick. Right down in the bottom, there's numbers in the 12,000 range. All right, so here's what we're going to do. We're going to take each number in the triangle and we're going to divide it by 2. Now, some of these numbers are perfectly divisible by 2. What are those numbers called? Even numbers. And the other numbers are going to have a remainder when you divide by 2, and those are called odd numbers. So what we're going to do is we're going to color the hexagon one color if the remainder is 0, meaning if it is perfectly divisible by 2, and another color if it's odd. But we don't need to really have colors because you can just let white be one color and then whatever pen or pencil you're holding be the other color. So essentially, all I'm asking you to do is color in all the even numbers. Okay. Every one of these even numbers, color one color, and if you're ambitious, color the other ones a different color or just leave it blank. Okay, what do we notice when we color in the evens? Do you see triangles that you weren't aware of before? Just looking at the even numbers, we see these upside down triangles, right? That were there, we just didn't see them until we drew them. And what do these upside down triangles look like from today? Looks like Sierpinski's gasket. And if you just do more layers of this thing and then zoom out so that you kind of lose track of the numbers themselves, you will see Sierpinski's gasket, which is kind of crazy. So let's take a quick look at a prettier version of the thing that you have. So here, I'll make this a little bit bigger. All right, so this is Pascal's triangle. You just have to tilt your head to see it. So for example, if I look right here, what am I looking at here? 1, 3, 3, 1, see it? 1, 4, 6, 4, 1, yeah. So it's just Pascal's triangle, but tilted. This triangle, this document was created very easily. First row is all ones, first column is all ones. How do you get this number right here? You just add the one to the left and the one above. And that's exactly what the formula says. Just add the one to the left and add the one above. And that's what they all say. How do you get this one? You add the thing to the left and you add the thing above. And so it's really just a matter of type the formula in once and then just drag it and drag it and drag it. Okay, so there's the triangle with many, many, many more rows than you have on your paper. And now what we're going to do is take a look here. So here's the same exact triangle. I'll zoom in a little bit. But what are the only numbers in this triangle? Ones and zeros. These are the remainders when we divide by 2. 0, if the remainder is 0, what kind of a number did we start with? It was an even number. So all I've done is change the even numbers to zeros and the odd numbers to 1. Okay? And in fact, you can even see there's this command in Excel called is even. Is the number even? If it is, put a 0. If not, put a 1. That's all it is even. Okay, so this is just zeros and ones, right? There's no funny business. All I've done is instead of coloring things in like you have, I put zeros, all right? Now all we're going to do is zoom out just a little bit. And something's going to start to happen with your eyes with these zeros and ones. Anybody starting to see? Do you start to see these triangles? Right? And it's okay if you don't see it yet. We'll keep zooming out. How about now? And we can see these triangles, and there's no coloring happening here. This is just literally like how zeros and ones look different, and we can see the triangles jumping out at us. Now I'm going to come over here. This is the same picture, but it's got more, so I can zoom out even further, right? And we can just keep zooming out, and you can see exactly what you've drawn. Yeah, that's better, right? There's no coloring here. All right, so this is my favorite part right there. Is because the ones take up so few pixels that you can't see them. So even though it looks like this is completely blank, what is that really? This is just a whole big, huge triangle of nothing but ones. But it looks blank just because there are fewer pixels to draw a 1 than a 0. And that, my goodness, that's Sierpinski's triangle right there. Okay, here's the same picture, but colored in. So where we saw all the zeros before, we now see, or all the ones before is now red. Well, what we did before was we just looked at odds and evens, because we divided by 2. But we could just as well divide by 3. Now, there are more than just two kinds of numbers when you divide by 3. There are numbers that are perfectly divisible by 3, like 6 and 9 and 12. Then there are numbers that have a remainder of 1, like 4 and 7 and 10. If you divide by 3, 4, 7, and 10, they all have 1 left over. Aren't there other kinds of numbers? Ones that have a remainder of 2, like 5 and 8 and 11. So all we're going to do is look just at the numbers that are perfectly divisible by 3, and we're going to color them in like you guys did with your even numbers. And so I've got a little slider up here. Currently it's on 2. So this is the picture that you have in front of you. But all I'm going to do is change it to a 3. And all these shapes are going to change. It's still only 2 colors. I'm not having 3 different colors up here. All I'm doing is coloring the ones that are perfectly divisible by 3, just like you colored the perfectly divisible by 2 numbers. So here it is, which doesn't look all that different. I'll put it back. The triangles have shifted a little bit, but you know, if you just showed me this picture and said, hey, Ian, what's that? I'd say, oh, it's Sierpinski's gasket. All right, now we're going to look at the ones which are perfectly divisible by 4. We're going to make them red. Here they are. Here are the ones divisible by 5 and by 6. And there's this strange behavior that I don't know about it. I don't know how much it's been studied, but there's something going on here, right? Like that's a really uniform distribution of all these triangles. That's when the number is 7. But when it's 6, they got all these different sized triangles, right? With 7, I only see 2 sizes of triangles here, and then maybe a third one, the real tiny ones in the middle. Okay, let's take a look at 8. All right, 8 is a lot of variation. There's 9, some variation. There's 10, lots of variation. There's 11, not very much variation. So let's go back and do some analysis. We're just going to keep track. Everything's divisible by 1. We're going to keep track of the ones that have really only the 2 different sizes of triangle. All right, so that one looks like a lot of different shapes, right? A lot of different sizes. That one's got a few different sizes. So that one to me felt like the first one where something was a little bit unusual. Can we just keep track of the numbers here? So 5 is the first one where it's really just like big one, and then these, I don't know, like I don't know how to describe it exactly, but I just feel like there's like more order or fewer different kinds of triangles there. Okay, that one looks all crazy. 7, kind of look like 5. All right, that's kind of crazy, crazy, crazy. 11. All right, let's keep going here. There's 12. There's 13. What kind of numbers are you guys writing down? Alicia says they're prime numbers. 5, 7, 11, and 13. Yeah? Prime means what? Not divisible by anything except 1 in itself. So the only things that go into 13 are 1 and 13. Whereas 12 has a lot of divisors, right? 6 goes in, 2 goes in, 4 goes in, 3 goes in. All right, so then if this is right, then what's the next number that should look like this? 15? 17 is the next prime. All right, so let's see. So, all right, lots of shapes, lots of shapes, lots of shapes. 17. 19 is the next one. All right, there's lots. 19. So it's really strange. Like I feel like there's this like extra order on the prime numbers that doesn't exist on the other ones. 23 is next. There's 20, 21, 22, 23. In fact, the prime numbers are another color in this room. I haven't looked at them yet, but look around. There are 4 different colors. Where do you find the primes? Just looking at the bottom rows. Just the bottom. The top row is just counting. You see the primes? They're the pinks. 2, you can't really see the 3. 2, 3, 5, 7, 11, 13. Those are the primes up there. Let's see, what's the biggest prime on my list over there? 71. Let's jump out to 71 and drag this guy way out here. 69, 70, 71. I don't know what's going on, but I think there's room for exploration here. Okay, that is good. Let's take a look back at our old friend, the triangle. So go back previous page because some of you guys have colored in. Okay, we saw the hockey stick thing. What I'm going to have you talk about now, it's another kind of pattern. So here's the basic pattern. I'm going to start with I'm going to start with this one, the last one that I wrote in, not the one that you wrote in, but the last one that I typed in. And to find the next number, I'm going to go up and to the right, and then straight to the right, 6. So up and right, and then straight to the right, okay? What's the next number? Up and to the right, and then straight to the right. Is the 10. See it? Go just follow the diagonal up to the right, and then go straight to the right. Put a dot. What's next? 4. Good. Yeah, 6 and 4 is 10. So what's the total of those 4 yellows? Is 21, adding them all up? Okay. So I'm going to use a different color. I don't know what you guys are going to do, but if we start on that other one, what's the next one? Just go up and to the right, and then to the right is a 5, and then a 6, and then a 1. Add those up. 13. Can you guys find the next few? Just keep going up that left-hand diagonal there. Just go to the next one that I haven't colored in yet. So circle them or highlight them or something, and then add them up. Good. Okay, what was the previous number? I've highlighted it in green here. Yeah, add up those green ones, we get 8. I circled in purple, 5 is the next one. Then I boxed in red as 3, and then I triangled in green as 2. Now I didn't go any further, but we could go further. What's the next number? Is the 1. I don't know, put a little star around that guy. And then what goes with the 1? If I go up and to the right and then to the right, there's nothing there. It's just by itself. So that 1 is just alone. And then finally the 1 at the top, right? What is this sequence of numbers? It's the Fibonacci numbers, right? 1, 1, 2, 3. You add the 2 previous ones. So there's all this, I don't know how to say it. There are all these patterns inside of Pascal's triangles. A really simple concept. Just add the 2 previous numbers to get the next number. But there are all these patterns, and like I said, we're just scratching the surface here, but somehow this thing has the Fibonacci numbers buried inside of it, embedded inside of it, if you just know where to look. Cool. Okay. All right. So. This is our last day of new material. We're going to end like 8 minutes early today. Shh. Don't tell anyone, my reputation will be ruined.
Aren't you recording this? Sorry.
All right, so we're all done with material for the semester. I think this is a good place to stop. Again, the project is due, so if you haven't done it, get it done soon. Lots of studying for our test, which is a week from Wednesday. We'll see you in 2 days.